All right, I think we're ready. We've got a couple of things today, kind of focused on functional, strong prints, how to make prints that you can actually use or at least put into service, maybe even if they're temporary. Um, got a little bit to do with Clipper because we still haven't ever added our start G code. We could work on that too. And then Monday, we'll have just an assortment of whatever last bits of things we need to do. Wednesday is the last day, and that's the one where we'll meet and do the catapult contest. All right, so let's see. Why don't we first? Why don't we first do the Clipper thing? So um, we've got everything runs. We've got the Clipper screen running. All that's working. What we don't have is we never have built a start G code so that when it starts printing, it goes and maybe does a purge. Well, it homes everything, does a purge line. So those are relatively straightforward. So it shouldn't take us very long, I think. Um, if we go over here, I have looked for sample. This is on the clipper3d.org site, and they have sample macros for the start print and the end print, and those are the ones that get called at the start of a print and at the end of a print, assuming you put into Cura to call them. So, or whatever your slicer is. So I don't know if I've done that. Let's see. Here's our printer. If we do manage. Oh wait, hold on. I might have started the older one. Let's see. Yes, I did. For some reason my shortcut link always wants to first do 5.4 instead of 5.10. I need to really switch that around so it doesn't do that. What is the size of the projectile we use? It is it's in the description. It's a particular one. It's a cat toy, and there's a link to it in the Canvas page. So let me go over there while we're waiting for this to start up and see if I can point you to it. Let's see. I assume I put it here, but let me see. And so the size is the default. Yeah, it's this thing right here. And you just print it at the size that it comes in. And so when you print this, that's all it is. It's about, I don't remember, maybe 1.5" diameter or something like that. But that's the print. You can use supports if your printer can't handle these overhangs at the bottom too well. Just make sure you don't put supports on the inside. That would probably be a pain to remove. Because it might want to put supports inside to support this top part. So if you do need supports for it to not, droop down here at the bottom, then when you select your supports in your slicer, tell it touching the build plate only. That way it will only put supports where it can build from the build plate, and so you won't end up with any in the middle there. But that's the thing. I think it's about 1.5" diameter. I don't think it tells me here, but that's what I remember when I printed it out. But yes, you do print your own though. So each person prints their own projectile. We were looking for sample macros. Oh no, we were trying to get Cura to run. That's what we were trying to do. So it looks like Cura started back. Manage printers. There's our Ender 3 with running Clipper. Machine settings. And so it looks like we've actually got that part built correctly. I don't remember. Maybe I did that. I don't remember. Let's check here. Not here. Here. So on this same clipper3d.org, this is the slicers section here. Installation and configuration, and then slicers. It gives you what to put in each slicer. So in Cura, put this line in there, which let's see if that's what I put in there or not. So just delete that and paste that. What this will do, first of all, it calls the start print macro in your Clipper printer config, and then it sends it these parameters. So it sends you the bed temp and apparently material bed temperature layer underscore 0, that is Cura's variable name for the bed temperature, and then extruder, same kind of thing. It just went off the page though. Yeah. And then these two are just zeroing out the extruder, so that's probably not doing much. Clipper may not even recognize those. So we've got we've got Cura set up. What we need now is a start print macro in Clipper to actually take advantage of this. And that's what we must not have. So if we go to our Clipper, here's our, we're logged into the machine, and we're over on machine, printer config right there. So one of these are all different macros. So there's one for Safe Z Home and Bed Mesh and Stepper X, and there's not one for Start Print. There just isn't. It doesn't exist in my list of macros in my printer config. So that brings us back over here to sample macros. So I click on that, it takes us here. Here is a start print and in print macro. So there's one for start print, there's one for in print. So we can just copy those, Control C, go back over to our machine, find us a nice spot, might as well put them at the top, and paste them in. And then let's actually read through them and make sure that they're doing normal stuff that we expect. So this line hopefully will take in the Cura's passing us. Hopefully it's passing this value over from Cura to Clipper. Otherwise, if it doesn't pass the value, it's going to start the bed at 60 degrees. Normally I print at 50, so I'm just going to put that as a default at 50. Here, same thing. It's supposed to pass the extruder temperature from Cura, whatever we have in there. Otherwise, if it doesn't get the variable correctly, then it's going to set it to 190. I normally do 205, so I'm just going to change those to what I normally print in case, although I guess I won't know until I change them if it's actually passing them or not. And then it sets the bed temperature. Here is our Z offset. Remember, we were having some issues with our Z offset. I'm going to set it 0 here because I believe in our extruder, I think we have a, maybe we don't have it there. Maybe it's in our BL Touch section. Oh no, it's commented out. So maybe it's down here in the, yes, it's down here in the save config. So currently we have it set down here. All right, so I'll leave that 0 in the start. Actually, I'll probably just comment it out so that it's not. No, let's leave it. Let's leave it that way. G28, that homes everything. So we do have a home line in there. This is telling the extruder to move up. Technically, it's telling the bed to move down away, because originally they were thinking the bed moved up and down on the printers that were running in the, I don't know, early 2000s, maybe late 90s. The beds moved up and down, and there are still printers today that the beds move up and down versus the gantry and, kind of a flying gantry kind of thing. Then it moves it really close to the bed, the nozzle, and then it waits for the bed to heat up, waits for the extruder to heat up. And so this does not draw a purge line. So if we wanted to draw a purge line, we'd need to add some stuff to this. So I normally do want it to draw a purge line. So why don't we write some code real quick for this to add a purge line. Normally what I want the purge line to do, and you can have all sorts of different things. Normally I draw it over here. You can draw it across the front. You could just set it to, purge out, maybe even off the edge if your printer will reach off the edge. Most of the time it just draws a line across here. It draws one and then it comes back and draws another one. So I am sure we could find online somewhere a place to download a purge line G code, but I think we can get away with just making one. So G1, well, first let's make sure that we're in a absolute coordinate mode. We are right here, this G90. G90 means absolute coordinates. G92 would be relative coordinates, like for your X, Y, and Z. So we are in absolute, so that's good. And let's put us a little comment that says draw the purge lines, just so we know what we're doing. G1 is a go at speed 1, which is your normal printing speed, versus G0, which is a fast travel. And we have homed, so line 31 here told us we homed, so that put us at 0, 0, 0, and then we moved the nozzle up 5 millimeters, but then we moved it back down to 0.15 millimeters, so we're sitting at 0.15. Okay, so in that case, we're already probably, let's move over a tiny bit so that we're not right on the edge of our bed. Actually, I don't know where 0, 0, 0 is. Why don't we go to the printer and find out? So I'm going to move, I've already homed it. I'm going to move X. Oh no, I guess I haven't homed it. All right, so let's home. Notice how quiet, or don't notice how quiet it is now. Looks like something, it actually hit the bed. I don't know if I've got, oh, there's a little bit of filament stuck on the bottom of it. I think that's what hit it. All right, now we should be able to move to 0, 0 and see where we're actually at. All right, so I got to move by smaller increments. Oh, it must have a, oh, never mind. All right, so there's 0, and it's really close to the edge of the bed, so I'm going to say that we probably need to draw our purge line at maybe, let's see what 2 does for us. Yeah, at X equals 2, so we'll just put, why don't we set it in the right spot first? So X2, we'll use capital. And let's start the Y at, let's see what makes sense on our printer. So Y, we're currently at 115. Oh, while I'm in, let's do bigger. All right, there's 0. And it's actually off the front of the bed, so that's not going to work. Let's see where it would make sense. Something like that. That is 13. So we will do Y13. So this little line, I don't know if it's kind of small there, line 41. We just wrote, can I zoom in? Oh, maybe I can. Yeah, there we go. I just wrote to move to position X2, Y13. So I'll let that be kind of its first movement. It just moves to that position. And it's still at Z 0.15, which is reasonable. You know, if we're going to squirt out a bunch of filament, a lot of times on the purge, you actually try to squirt out an extra amount of filament. And so having a distance of 0.15 is probably okay. We can always tweak that later. Now what I want it to do is, from its current position, I want it to go somewhere near the back of the bed. So in the Y direction, so I don't want to change X. I'll leave it at X2, and I'll just change Y to maybe something like, let's go back to our printer. Let's go by 50s here. Now let's go by 25s. I mean, that's probably good. That is Y188. Let's just do Y200. Let's see what Y200 would look like. More or less that. Yeah, all right, so Y200. Okay, but while we're doing this, we want filament to come out. So this is the part where you put an E for you want the extruder to run, and you have to calculate, and we're not going to calculate, we're just going to guess. Calculate how much filament in millimeters of filament passing through the nozzle. So not a volume or anything like that. You could figure out the volume if you knew the size of the nozzle, so that's the diameter, and you could calculate how much filament goes through there. But what you're actually putting in your slicer here, not your slicer, in your G-code, is the amount of filament that actually goes through the hot end in millimeters. So the length of filament that you're extruding. Let's guess a number. We're moving probably 200-ish millimeters, but we're extruding 0.8 versus the filament diameter is 1.75, so we don't need like 200 millimeters of filament. Let's try, I don't know, let's try 20, maybe. I don't know. We'll try 20 and see what happens. Either it will be way under extruded, or we could go and look. This might be a good time to look for some purge line G-code to see what are typical numbers. Let's see if we can find one that's written somewhere. Let's see. Hey, that's actually close here, but they didn't do nearly as long of a movement. So they moved basically, they were at Y equals 10, so they did 40 millimeters, and they extruded 25. So kind of 1 to 2. So maybe we should do closer to 100. I kind of think that's a lot. Let's do 50, and we'll see what happens. Normally when you draw this purge line, the first bit, there's no filament in the nozzle, so nothing's actually happening. So you draw the first line, and maybe half of it prints, and then you step over. So we would go over to maybe X 2 point. Let's see, our line widths are 0.8, so 2.8. So we just moved over, and then you come back to where you started. So back to Y of, where did we start? 13. So we can come back to Y. I like nice even numbers. So 20. Let's change this one to 15 because I don't know, it just bugs me. Make them both, it comes back to where it started. And so this is a confusing part here. We want to extrude filament on the way back also, but you wouldn't put E50 because remember, we're in a absolute mode right here. We're in absolute coordinates. That counts for the extruder too. So it has already gone 50. If you want 50 more, you have to add 50. So E100 would add 50 more millimeters of filament through the nozzle. So that sometimes confuses people because you think the extruder, you don't think of it as also having absolute or relative coordinates. So since we're in absolute coordinate mode set on line 27 up here, then that counts the extruder too. So these little lines here should draw us 2 purge lines. We may not have enough filament going through them. We may have way too much filament going through them. But it should draw us 2 purge lines. They are currently, the nozzle is 0.15 millimeters above the bed. That's probably reasonable. We might want to raise or lower that. But now we have a start G-code that draws a purge line, and then it's going to wait for the print to start. Or, well, actually, it should start the print right after it draws the purge line. You could do other little things, fancy purge lines or whatever, but that's if you had a nozzle cleaner, like a little brush that cleaned the nozzle, you could go park over there and clean the nozzle off, all kinds of things. In print, basically it turns everything off, moves the, oh, I said G92, it's G91 is the relative mode, not 92, apparently, because this has G91 in it. Let me check on that. Yeah, G91. Okay. I said 92. So 91 is relative positioning and 90 is absolute. Here you got some negative numbers because we're relative now. And so it's wherever you were, just subtract off 2, subtract off 2, subtract off 3, even on the extruder. So that's kind of like a little retraction. 3 millimeters, we are on a direct drive. So 3 millimeters is a bit for that, but it should be okay. And then these F numbers, these are how fast do you want to do things. If you don't specify the feed rate F, then it just does whatever the default is, or whatever it was last set at. And then it goes back to relative, turns off the steppers so that you could move things around manual if you wanted to. So that's fine. We don't need to do anything fancier than that. So we've got our start and end G codes in here. We can save and restart. Now if we try to print something, we should have a purge line and some homing. We don't have to do that on our own, hopefully. Let's get this back to a reasonable size. All right, so that's that's the same kind of thing as if we wanted to do some firmware updates. Although the purge line, you could throw in your slicer and just add it to the beginning of your G code. That way you wouldn't have to change your firmware to change the purge line. Alright, now we've got that set up. Let's look at some of the ways that we might want to print functional parts. So the whole quarter, actually since maybe January, I've been using a 3D printed mouse. Well, so actually this part is all printed, but there's a little kit. I probably showed you at some point the kit. I don't remember if I did or not. I'll see if I can find it really quick. It's from Maker World, but Maker Supply, I think it's in here. Yeah. So if you go to Maker World, up at the top, there's let's get that where you can see everything. It's off the screen. There we go. There's a let's go back. Maker Supply, and that takes you over here. And I don't remember which one it's in. It might be in model kits, maybe. Let's see. Maybe. Oh no, there's more. Maybe I need to search because there's a bunch of them. Yeah, there it is. All right. So, is that the same? That's a slightly different 3D model than what I have. But there's a little, all the guts, that you can buy, $13, I think. Yeah, $13. And you can build your own mouse. You can print all the surroundings around this. And so I've been using that for, I'm pretty sure since sometime beginning of the year, January-ish. And there's different versions that you could do. I think that's the one I did. I didn't see these other versions at the time, but I did that one. And so this one has already been kind of set up. Now I did use silk filament, silk is not normally good for things that are going to function because it has not as good layer adhesion. But really the only thing that moves are the buttons here, and they don't move a whole lot. They barely flex. Now it does print, I think it printed standing up like this. Like this, I guess. No, probably like that. And so the layer lines are going across the direction that it needs to bend. You have to push here or here. But it's worked fine for months now. And I suppose if I wanted to change it, then I could just reprint it. in a different material if it broke, or the same material. So you can create functional things. There are a couple of ways that you might go about doing that. One of the questions earlier was, does it work to anneal PLA or a 3D printed material? I'm in the process of that, and I thought, well, we probably should be able to mechanically test. Is it better if you print a thing and you anneal it, and is it going to be actually stronger or not? So going back over here, if you want to know those things for real, there are standards for testing anything. So the standard for flexural properties of unreinforced and reinforced plastics and electrical insulating materials. So this is ASTM, and they are the the main place you find these standards, the correct, the agreed upon way to test different materials for different properties. So this one is a flexural property. There would be another one that's the tensile properties. So this happens to be D790, if you can see that. So D, the way ASTM numbers these things, the letter, in this case D, corresponds to the subject area. So D is miscellaneous materials, including plastics. So if you have some kind of metal, then there's an A for ferrous metals, and B is non-ferrous metals, C is ceramics, D is the miscellaneous stuff, and it goes on and on. And so we're in the D category because we have plastic. The number, in this case 790, is just the specific thing, like flexural properties or tensile properties or whatever. And then that -17, the number at the end is the last revision year. So this would have been last either created or revised in 2017. In fact, it says right here, last updated July 24th, 2017. So the only problem with this is that this part over here. So the actual standards, to see what is written in the whole thing, is not free. ASTM is an organization, and they maintain these standards, and you need to follow these standards if you're trying to accurately test something. And so they sell them. So this particular one is $76. Now, fortunately, usually the older versions of these standards are usually pretty similar. They don't drastically change things normally. And you can usually find an older one just on the internet somewhere as a PDF or whatever. And it's going to be close enough for what we're going to do. But if we were in industry actually testing something, we'd need the most recent standard. You'd want to comply to the most recent standard. But since we're not actually, doing anything, we just want to test our pieces of plastic, then an older one will be good enough for us. So here's one that is actually this one's almost as new. This was 2015, so I don't know what they changed between 15 and 17, but this is the type of things that would be in there. And so you will have a summary of the test method. Sometimes if the test specimen is really complicated, they'll have a drawing of the specimen. Now this particular thing is setting us up to do a 3-point bend test, so the specimens are just rectangular. And somewhere in here they'll tell us, let's see, there's the test apparatus, so I probably missed it somewhere. What's right where I highlighted summary of the test method. The first thing they tell you is the specimen. Now we are in a gray area here because we have 3D printed this specimen, and that probably falls a little bit more into a laminate. Layers stacked on top of layers is what we're doing when we 3D print. And they do say that unless you're testing certain laminated materials, if you are testing certain unlaminated materials, you might need to go follow a different standard. since we're not being super picky right now, and I think we can get away with not worrying with the laminated beam theory kind of thing, we'll stick with assuming this is a bulk material, even when it's probably not, or it's somewhere in between. You know, it's not quite laminated, but it is not just a solid extrusion either. So we're somewhere in between those. So what this is telling us is basically a support span to depth. In this case, depth is talking about thickness of the little rectangle. Oh, it does say it's going to be rectangular cross section, 2 supports, flatwise position, so it's laying down across these 2 supports, and you load it with a loading nose, so a point in the middle, and that's your 3-point bend test. There's 2 supports and 1 loading. There is a 4-point bend that has 2 loading noses, but this is just a 3-point bend. And it tells us a general size ratio. So the span to thickness of our beam is 16:1, shall be used. And then you run it until you either get 5% strain or it breaks. I suspect with ours we would probably get to the 5% strain first, but I don't know. It also depends on the orientation we print. So we just got to make a little rectangle. I did go and see if there were some other like exact dimensions that were common. Let's see if this has a picture of our. There's a little tiny picture of a 3-point bend test right there. This one did start to give some actual dimensions over here. 3.2 millimeters thick, and then 12.7 wide, so half an inch wide, and 127 millimeters long. I assume, I didn't calculate it, I assume the 127 over 3.2 actually is 16. Let's see, I don't know. That doesn't seem like that's going to add up right, but maybe it does. Let's see, need a calculator. 3.2 times 16 is only 51.2. So that doesn't give us our 16:1 ratio there, but and this is D790. Oh, okay. So they're just saying this, it's going to overhang, right? Because you can put the little supports, the 2 supports, at any distance. You wouldn't want to make the specimen exactly that length. So you make it this long, and then you set the supports at 51.2 millimeters apart. That's what it's telling us. Okay. So why don't we make some of these? I think it's just a rectangle. We can make that in Cura. So Cura, oh yeah, we were in Cura over here. So we should just be able to go in here and drop in a cube and then resize the cube. Not move it, but resize it to be, what were those numbers? I've already forgotten. 3.2 in the Z direction. I think in the X direction it was 12.7. Now we might want to rethink some of these dimensions, and it was I think 127 in this direction. No, oh, it's uniform scaling. So let's fix that. There we go. Oh well, it looks like I've got them. I'd rather print it laying down flat, I think. Oh, I put 1.7 also. So 127 that way, 12.7 that way. There we go. There's our little test specimen. Now, one issue that we would have here is our 12.7 is not easily divisible by our layer heights, right? So if we make it 12.6 though, right? If we do 12.6, that will divide. We currently are at a 0.3 layer height. I think it would divide evenly then. Now we have to decide on, are we going to print a solid specimen or some kind of hollow thing? currently we have two walls. Now again, we've got the 0.8 millimeter nozzle, so these are thick walls. But we've got two walls. We've got 3 top and bottom layers. Let's slice it and see what it looks like first, and then we'll make some choices. So there is a little bit of infill in there. It's kind of haphazard infill. It would probably be better if we use one of the more periodic infills instead of lines. If we use maybe gyroid, or oh, that's the top and bottom. Where's the infill? If we use gyroid, maybe that would be a little more uniform on the inside. So if we think about what 3-point bend is doing, right? 3-point bend is going to put tension on the bottom, compression on the top of the beam. The middle part is going to have, well, the very exact middle is going to technically have no strain, and then there's more and more strain at the top and bottom, and therefore stress. So the middle is not doing as much, right? It's just trying to hold everything together, though. So there is some transverse stuff. And currently it's taking 13 minutes. Let's just see how many. We have 10 layers. Let's see if we do 5 top and 5 bottom. How long is it going to take to print that? It's not that much longer. It's 17 minutes versus 13 minutes. And now we've got a solid block. Now, notice something here. You can actually control this if you want to, if it matters in your trying to create a certain type of property, strength property. Our layers are going back and forth. See, they're kind of alternating back and forth. You can actually control that pattern if you want to. So I think we probably have to open up our little extra menu here. Oh, let's see. Which one is it going to be? Oh, maybe you can. I think. Do you have to do it in the infill? There's the pattern for the initial layer, and there's a pattern there, but that's not the pattern. Oh, here we go. Line directions. So that, and we need one for top line direction. Now that's the very top surface, though. For just the skin layers, I really like only the very top one. I might have to dig to see where it is, but what you can do when you find it is, let's see if it put anything useful in here. It did not. Oh, I didn't turn on the other thing. So you can actually put in the orientation in degrees for each layer, but it may only show up in the infill. I'll have to dig deeper to see which one you have to turn on to have that. But if you need to, maybe you need all of these pointing the same direction, or in some different patterns or whatever. You're trying to intentionally laminate something in a certain way. You can change that direction for those patterns. I'm just not seeing it at this very exact moment to do that. So I think we've got, one test specimen there pretty well. Why don't we save that and print it? This will also test our start G code. Let me clean off the bed here. It looks a little dusty. Do I have some of my spray? Yes. Now, I have not recently set the Z offset on this, so there is some potential issue that we still need to work on there. This will be, I'm just going to name it ASTM D70. 790 rather, 790. And we'll save it on the desktop. All right, to print it, we need to find this. No, not that. Close that. That one. G-code files. We will upload our ASTM D9 790. It was on the desktop. Oh, there it was right there. And then we'll just print that and see what happens. So I see that it set the target bed. I didn't even check our, I didn't check our temperature in Cura. The last thing we printed, hold up. We've got some problems. All right, so this will happen to you. Let's cancel that. So Cura, this is not Cura, this is Fusion. Cura, it remembers the last thing you did most of the time. And what was the last thing we did? We printed with the arrow filament, which expands a lot. So I probably did not go in. First of all, I'm printing at 220, which is a little hot for this. Let's go to 205. But the other thing is we changed the flow rate. All right, so maybe I did change it back. I was afraid that I had left this at 30% or 70%, whatever we did. Looks like I changed it back, so I think we're all right. All right, so, but we were printing a little bit hot. Let's go through the layers again. All right, that looks good. And let's just overwrite the old one. And then let's go back to Clipper. It has stopped, like I told it to pause, but the last command it got was to get the bed up to 50 degrees. So it is going to wait until it gets to 50 degrees before it goes to the next line of G code. And then I can interrupt it to actually cancel the print. I suppose I could like turn it off or something, but we're at 49.3 degrees, so it's going to be fast enough to just shut it down there. It did pass our values because there's the 220. Oh, that means it had already queued the 220 temperature, so we've got to go to that too before we can cancel. You know, I think we can just proceed though, because I can just manually change it here. So what I clicked over here was the pause button. Once it gets to 220, hopefully, I think it might have already queued the homing routine also, I suppose. We can just carry on instead of actually canceling it. I think that'll be fine. 220 is not terribly hot for PLA. It can print at that, and we can just lower it down. One of the things that you can do to make stronger parts, printed parts, is to print hotter. So that would kind of be an interesting thing we could do, is print this same exact specimen, same material, but print it at different temperatures and see if we do get better layer adhesion at higher temperatures. You know, technically you should, because the filament is melting better to the previous layers, but that wasn't what I intended. All I wanted to do was print print some of these and anneal some and leave the others normal. So I want to, that's the variable, is annealing, not print temperature. We could have that later. If you could do that. We won't have time in class to do that. Oh wow, we got some okay, so it didn't like some of our extrude distances, the E values that we put in there. It didn't like some of those, probably in our purge line. So it skipped them and it went straight into printing. Or no, what's it doing? I think that's the pause. That's the pause routine. Okay. Let's see if it. There's the home. I did not change our start G code with the purge line, so it might crash again. We'll see. I don't know if it'll just go past it and just decide not to extrude anything on the print, on the purge line, or what it'll do. We'll find out shortly. It's got to heat back the nozzle. Doesn't take very long though. It's already got the bed heated up. It overshot quite a bit. I think we did a PID tune on this, but maybe we didn't. I think we did, but it did overshoot quite a bit. I'm also noticing that it's heating with the nozzle basically right over the middle of the bed. I don't really like that. I don't like the nozzle, the heated nozzle, to just sit right above the bed. It's basically on the bed. Alright, so it did crash. Let's go over here and let's fix this. So, let me move. There we go. So here's the error I'm getting. Basically, it says that when I asked for it to extrude for the purge lines, let me go ahead and set these temperatures so that we don't have to wait on it. I asked, apparently, I didn't calculate it, I just guessed a number. I asked for it to extrude a 0.65 millimeter squared amount of filament, and somewhere in a configuration file in the max extrude cross section, I've got it set to the maximum I can do is 0.64. So apparently I was close to the maximum but a little over it. So to fix that, let's just go to machine, printer config, and here, instead of asking for 50, let's do it, and 50 must be like the maximum. Let's just do half of that, and then that means we need to drop that down. Save and restart. It's restarting Clipper, and let's try to reprint this file. It's already mostly heated up, so let's see what happens now. It's doing its homing routine. And see, I would like to, instead of going and heating up the nozzle now, I would like to move it over somewhere and raise it up a little bit off the bed, then do the final nozzle heat. Because I don't really care for the nozzle heat right there. You do, if your Z is dependent on the bed, you know, you don't have a little switch over here that controls your Z height. If you're probing off of the bed, you do want the bed heated up to printing temperature before you do your Z home, because it is possible that the bed is going to warp on us. Oh, all right, so look how slow it's moving. So I did not specify a feed rate, so it is using the travel speed is the feed rate. I didn't specify that, so it's using whatever the last feed it was given, which apparently is really slow. So we could go in there and definitely add a F2000 or something to move quite a bit faster than what we're moving now. It's happy, it's making the purge line, it's just going really slow. Nothing's coming out, so I think we're probably too close on the bed. Alright, so there's our first little blob of filament that has come out. There was the little shift over, and now it's coming back again, way too slow. We need to speed up the feed rate. Unless you really, really need a really slow purge line, which you don't. I'm just waiting for it to make sure it's going to get the first layer of the print. So there's a more reasonable printing speed. That's a relatively thick line, but remember we do have a 0.8 millimeter nozzle in there, so it's going to be pretty thick. Now what I'm seeing is that this side is really thick, that side over there is not. So the bed is not completely flat with our motion system. You can see over on that, I don't know if you can tell or not, I think you can, that this side of the skirt over there is not nearly as thick as this side. So it's the same amount of filament coming out, but it's getting squished further this way on this side versus this side. I actually like this side more. So what's this? This side is too high. I could just pull it down a little bit on this side and adjust it that way. I've not leveled this bed since we've rebuilt stuff, so I do need to go and level the bed with all our motion system, and then we can do a bed mesh with the CR Touch and all that. So it looks like it's going to print. Got some little weirdness in there, but it looks like it'll print. All right, let's go over and just talk a little bit about some different things you can do. So we're going to see if not immediately, because we have to do the annealing process, and I need to print maybe 6 of these, 3 for annealed and 3 for unannealed, and we won't be able to do all that today, but we can at least get started on it. But there are other things you can do to strengthen your parts too. Sometimes you're making functional parts and you need to assemble them. Last time we kind of talked about different glues, a super glue versus an epoxy kind of thing, but sometimes you don't want to glue it at all, and there's a variety of ways you can use fasteners, like metal fasteners. So we'll look at some of those down here. This is my little test block that I use. So one thing you can do is you can print pockets the shape of nuts, hex nuts. The hex nuts are kind of your default, because you can just go to Lowe's and buy those, or wherever you're buy hardware at. You can just buy those. Most of your CAD programs have a hex shape built into it. You do have to give a little bit of clearance. You can't make it exactly the same size as your fastener, but you could print just a pocket like that, or a lot of times you can do the pocket like this, pause the print, drop in the fastener, and then print over the top of it, and it's captured in there. So the downside with these is that they can relatively easily round out this hole. If you're putting a lot of torque on them, they can relatively easily round out the hole, and then it's not doing anything. So let me see if I can find them. I should have looked them up ahead of time. Let's see. Not these. Okay, these. They make rectangular, these are usually to go in the slots of extruded aluminum, but they make a lot of these little rectangular ones, and they are threaded. So they're usually smaller, so they're not the size of what I was using over here with the 1/4 inch or whatever that is. So they're usually smaller, but these will capture in one of those holes much better than a hex nut will. It's going to be really hard for one of these to round out the hole that it's in. Or you could just make these, get you a piece of flat stock, cut it to whatever length you want, and drill and tap whatever threads you want in it. So this kind of shape is a little bit better than the hex nuts in the sense that it is less likely to round out the hole that it's in. This is already kind of round, and if you don't have super tight tolerances, maybe your corners in the pocket are rounded, so It's not hard to round these out. You can just print threads into the plastic, and that will work. Definitely doesn't have quite as much holding power as the metal threads do, but you can do that. Most all of your CAD programs have a thread generator, or have a macro you can add in for a thread generator, and you can actually generate the threads that match whatever your fastener is into the plastic. And assuming your layer height is reasonably small, then it can resolve, threads like this. It can resolve threads of that nature. Maybe you do have to use a coarser fastener instead of a fine thread to resolve the threads in the print, but you can do that. There are screws that are specifically made for plastic. Notice the different thread profiles on these two. The silver one is a machine screw made for going into like a nut, and the black one has a much coarser thread, and it's a higher pitch, so there's a lot of distance between the threads, adjacent threads. There are specifically screws made to go into plastic, and they look more or less like this kind. They have the really coarse pitch, they have deeper threads usually, and there are usually fewer of the threads. You do have to get the holes right. I just kind of guessed here, and you can kind of see how that one pulled out. Like it didn't, that hole is a little bit too small for that fastener. You can create little slots in the sides where you drop in a thin nut, so like this one, but thinner, and you can, this, can't get it out of there. I don't think there's a nut in there right now. I think it's just, maybe, let me see. Yeah, I don't think there's one in there, or it's not coming out anyway. This is a pretty popular technique because you don't have to stop the print to put the fastener in. You can put the fastener in later. The Prusa printers use this a lot for the way that they fasten things together. So you put a little nut in here. The one thing you have to worry about is the top surface sagging. So you do have to have a printer that bridges really well. But this is usually not a very long bridge, and so it's usually okay. Maybe my favorite thing is this kind of a heated thread insert. Let me show one not in there. So here's a bigger one, I guess. They're this kind of thing. That's tiny. Let me see if I've got a bigger one. Here's some relatively large ones. Can't get them out of the bag though. Actually, that might be what's in there. So these are usually brass, so they conduct heat really well. They are metal though, so they have metal threads in there, and they've got some type of ridges. This one is they're just vertical splines, but there's some kind of rough surface here on the part. You print a hole. You take something like a soldering iron, and sometimes there are special tools. I have one set here. I have a better set, but I don't know where it is right now. Let's see. Nope. This one. So this would go in or on your soldering iron, and it's just a brass. Maybe that's copper. No, it's probably brass. End that would heat up, and you push the heated, the warm threaded insert into the plastic, and it will melt its way through. You can kind of see on this one, my temperatures weren't quite right, and it kind of indented. Generally, you want whatever you're heating with, so your soldering iron, to be just hot enough for it to start sinking in there. If you put so much heat, like if you crank your soldering iron up to soldering temperatures and do this, it's often going to be that the heated threaded insert will just melt through the whole piece of plastic. So you do have to be careful that you don't overheat it. But these are really handy. They don't hold a lot of torque, not as the kind of torque that a real fastener would hold like this, but they hold enough that you can clamp things together. You don't have to stop the print. You just print the hole. You do get metal threads. You don't have to deal with trying to get a little nut down into a hole somewhere that might be not perfectly shaped. So these are kind of my favorite things if I need actual metal threaded fasteners. I kind of like these the most. But there's a lot of options of ways that you can go about getting a better way to fasten things where you can take it back apart later. You can do snap fit type of things. In general, the snap fits, like Fusion has a snap fit tool that you can use to make the geometry. Most of those are set up for something like injection molding, and it's not really taken into account flexing 3D prints. Thin 3D prints is not always the best thing. But there are some snap fits you can do. There's actually one in Tinkercad that works pretty well. Let's see if I don't have Tinkercad running, but it doesn't take. See if we can get to it really quick. I keep having to move. Well, maybe I can just move Tinkercad. Yeah, there we go. We'll just make it smaller. So over here, I gotta remember where it's at. Might be in hardware. Let's see if it's in hardware. Yeah, well, there are some in here. There are some pre-made snap joints. This is not the one I was thinking of, but there's some pre-made, kind of like a ball and socket kind of thing. Let's see in the more shapes. There's a couple of those that are already built in Tinkercad. Maybe in machines? No, those are actual tires and things like that. Well, so if you explore around in Tinkercad, there are some pre-made snap fit components that you can add to whatever. Maybe it's in design starters. I'm not sure where it's at now. I wonder if there's a search. Oh, search. Let's search for snap. Yeah, these. So there's a snap fit. Now the thing that I'm not seeing currently is that most of these they have a matching hole cut out, like the negative space that you use that matches this one. It's got the tolerance built in and everything, and so these work relatively well. 3D printing in general. I don't know about that particular one, but I have used several of them in the past. I'm just not seeing where they're hidden in here. Yeah, you'd have to look through a lot of these to find out. I would assume they're probably in the hardware, and maybe we just didn't look deep enough into some of these. There are certainly some in here. I don't want to spend too much time looking for them. I think they're in here. I'm seeing things that are similar, but I don't see the our print finished. I don't see the exact ones. So you can do snap fits. The ones in Tinkercad work a little bit better than the ones in the actual big CAD programs, because the big CAD programs like SolidWorks and Fusion are assuming you're injection molding this. Let's look at our print over here and see how it came out. So I'm noticing one thing is that we are definitely over extruding. Let me show you. See if we can get in on that. Maybe if I pick it off of there. Wow, it's stuck down pretty well. So we're definitely over extruding. Either that or we're not moving in the Z direction the right amount. Let's see. I told it to be, I don't remember now. I told it to be, what was its size? 12.6 millimeters thick. So let's check and see what we're at. Oh no, I told it to be 3.2 millimeters. Actually, it's over that. It's 3.41 millimeters. 3.28. And it's definitely over extruding on here. That top is not very clean. Let's see if we're close on these other dimensions. That one's 12.76. It's supposed to be 12.6. Again, a little bit over extruded. Let's check on our length here. 127.24. Supposed to be 127. So X and Y are pretty good. Z's a little off, but it's definitely too much filament coming out. So we did check our, now Clipper doesn't use E-steps, it uses rotation distance. We did check that, but I think we probably really need to confirm that I haven't changed something since then, but then we need to work on our flow rate. So we've also got too close to the bed. That's really, let's see, can it, there we go. You can kind of see in the middle of the screen there, that part that sticks out. You can see how bad that it's squishing that first layer, way more than it needs to. So that means our nozzle is too close to the bed to start with. It definitely stuck down fine, but our nozzle is too close to the bed, and that first layer is really squishing out. So we need to work on our Z offset. We need to work on our flow rate, because I switched it back to 100% after we did the arrow, and it probably needs to be 90 something percent. So we need to back off on the flow rate. All right, so my plan is get it tuned better, and we could test this, but I think we can do better. And print 6 of them, anneal 3, and then I'll take them to school, and we'll see if the annealing, made them any different in strength. Let's see. What else was I going to talk about today? I was going to talk about some stuff in Fusion on like just design thinking for 3D printing, but we might have to save that till Monday, because we only have a few minutes left today. So I think Monday what we'll do is we will, I don't guess I'll be able to test the prints before Monday, because I need to be at school to do that, and I won't go over the weekend. So we will do some design thinking for 3D printing. There are, if you intend to design something that's going to be 3D printed, it's not like a prototype or a test fit or something like that. It's going to be 3D printed. There are things we can do to make it more printable, make it stronger if it's 3D printed, some considerations, and we'll talk about that. We should have our parts annealed. I don't know if I'll have maybe I can figure out a way that we can test them here. I don't really have a testing machine here though, so I don't know how that part will go, but we'll see. And then Wednesday we'll do our catapult test. All right, I will see y'all on Monday. See y'all on Monday.